Hi, this is Dr. Champion, and I'm going to be talking to you about the chapter here on electronic structure and periodic properties, which is chapter 3 in the OpenStax Atom First 2 edition book. I've got the screen here now on our OneNote file, and I'm going to be writing some lecture notes on that. You can see on the OneNote file here we've got this screen, which is a printout of some PowerPoints that Dr. Russell prepared, and then that's on this tab, which is cleverly labeled New Section 1. Let me change that right now and call that Chapter 3. Okay, and then over here on the side we've got pages. So the first page is the PowerPoints, and then the second and third pages and so forth are example questions that are going to be showing up as assignments for you in the class. So those are all there, and we can probably talk about those in the same way that we're talking about these slides. So my goal in this one, we're going to start with trying to get through slide 34 of this. So I'm going to go over here to draw and make sure I'm set up to draw. I may come back to that periodically, and so we can start going through these slides. So here we see some instructions that Dr. Russell is giving you that so you can read those here and see basically that 3 to 34 are concentrated review of the classes you had before text. So this material is going to be some review for you, and then we're going to go on further into this, like I said, those practice questions are going to be something that you'll be submitting as an assignment. So what happened in the early 1800s was that folks started to be doing experiments with light, and eventually into a little bit about electricity. And this is one of those things where we usually think about science causing there to be developed technologies. This was the fact that technology was leading to the observation of new phenomena that science had to try to explain. So one of the things they talked about was that if you took light and you passed it through these closely spaced slits, which would be like passing something through a prism, it's kind of an analogous process, that creates interference patterns. Of course, if you put light through a prism, it breaks into its component colors. Those interference patterns and the breaking into colors and all like that, the way folks explained that was they said, okay, well, light's got to be a wave, right? A wave kind of looks like this, like so. And I'm not drawing a very pretty wave here, but that sort of thing. And a very bright man, James Clerk Maxwell, who basically said that there's a whole range of electromagnetic waves, and light's just the visible part of that spectrum. And then later on, there was other experiments that you'll read about or hear about in a few minutes, that when you tried to explain it using light, saying that light's a wave, it didn't work. And so folks looked around, and there was another old theory of how light might exist as particles. And so there were some things you could explain using particles, some things you could explain using waves. Eventually somebody put the two together and said, okay, there's this idea called wave-particle duality, that when you get to really small things that are going really fast, they're going to have both a wave nature and a particle nature. And sometimes we'll need to think of them one way, sometimes we'll need to think of them another ways. And this is characteristics of an intelligent person, of a scientist in particular, is the ability to be a little flexible in terms of how you think about things and say, okay, I don't know what it's really like, but when it's doing this, it behaves like a wave, and when it's doing that, it behaves like a particle. So the waves are, again, electromagnetic waves, and that was something that Maxwell was a big part of later on, and you'll learn about more in your physics classes when you take it, is that light and things like light are generally called electromagnetic waves. They have an electric field and a magnetic field, they're both oscillating, and we can think of them as oscillating as a wave, so that up and down thing, and they're 90 degrees off from each other, so they're going in the same direction. One is, kind of in the Z plane, and one is in the XY plane, if you will. If you look at these waves traveling through a vacuum, they all travel at the same speed, which is the speed of light here, which is 2.998 times 10 to the 8th meters per second. That's a lot, a long distance, and a very rapid rate that they're traveling in that or very long distance they're traveling in that second. So when we talk about waves, we generally talk about three properties. We talk about wavelength. Wavelength is illustrated or labeled by this Greek letter lambda, which is that's the lowercase lambda. It looks like a Y that's kind of been rotated. Frequency is indicated by this letter that looks like a V, but it's actually the Greek letter nu, and that's the number of wavelengths that pass through a given point in a certain amount of time. So that's measured in peaks per time, or cycles per time, or just in per time units. And then the amplitude is basically how far up and how far down it goes, or as it says here, 1/2 the distance between the peaks and the trough. So if I'll sketch a poor drawing of a wave here again. So here's our wave, just looking at one dimension of it. If you want the wavelength, you can take two peaks. So going from here to here, this distance right here is the wavelength. It's moving in this direction at the speed of light, presumably. And if you stand right here, if I had somebody standing right here looking at this and counting, 1, 2, 3, etc., that would give us our frequency, nu, okay? And then the amplitude is, if the average position is this line right through here, how far up or how far down it goes, those are the amplitude. So that's kind of a picture of what a wave looks like, how we think about a wave, and frequency and wavelength and amplitude. So frequency, again, generally what we do is just simply say seconds, reciprocal seconds. Reciprocal, of course, means 1 over something. So 1 over s is s to the minus 1. That's also known as the hertz, as they say here. We will see megahertz and gigahertz, where you multiply that by 10 to the 6 in the case of megahertz, and 10 to the 9th in terms of gigahertz. And if you look at an old-fashioned radio dial, I don't know if any of you ever saw an old-fashioned radio dial like so in a car, and you had your AM band maybe was up here, and the FM band was down here, and your AM, like 1110 is the WBT station, and the FN band, you might I think 99.3 is the WBT station on that. And these are in kilohertz and megahertz, if I recall properly. If you've seen that type of old radio thing in a car, maybe you've seen that kilohertz and megahertz thing. Kilohertz, of course, would be 1 times 10 to the 3rd hertz. So if I were trying to figure out, for example, if I'm looking at WBT AM, which is at 1110, that means that I have 1110 times 10 to the 3rd hertz, and I could say that, well, that's 1.110 times 10 to the 6th hertz, we could go on and figure out other things about that once we learn how to do those calculations. And again, that's equivalent to saying 1.110 times 10 to the 6th seconds to the minus 1 there. All right, so here's one of the first formulas is that if we take the wavelength and we take the frequency and multiply it together, we get the speed of the wave, which is the speed of the wave. We are assuming usually that it's the c, the speed of light. So the equation is written a little up there, but I'll write it here bigger. Lambda times nu is equal to c, where lambda is wavelength and nu is frequency. And of course we could solve this for different things. So we were just looking at the slide before we had the frequency. If we wanted to know the wavelength, I could take both sides of this and divide it by frequency and cancel out frequency. So I get that wavelength is c divided by the frequency. So 2.998 times 10 to the 8th meters per second. And then if I use my frequency from the slide before, what I say, 1.11 times 10 to the 6th seconds to the minus 1. I could calculate what this is, and I want to explain a few shortcut calculation things here that might help you. First of all, looking at the units, I've got meters per second over seconds to the minus 1. That's a little easier to follow if we recognize that that per second up there can also be written as second to the minus 1. And so those are obviously the same thing. So this is going to come out in units of meters. The other trick I want to mention to you here is if I have 10 to some power, let's call it x, divided by 10 to some other power, let's call it y, that's answer to that part of it at least is going to be 10 to the x minus y. So I can tell that 10 to the 8th over 10 to the 6th is going to be about 10 to the second. 8 minus 6 is 2. 10 to the second is 100. If I do the other part of this, 2.998 divided by 1.11, I can see that's going to be a little less than 3. So I'm expecting an answer of around 300 meters, maybe, is what I'm going to get. Now, if I get my calculator out and actually do this, I'm going to start plugging that in. And there's a trick that I want to talk to you about. If you're using a TI calculator and you start typing this first number in, 2.998, instead of saying times 10 caret, so calculator, particularly the TI 80 plus calculators, you could say times 10 caret 8. That little thing there is caret. I'd really rather you not do that. What I'd rather you do is say second, comma, and that is together is what's called the EE button, and then just 8 to do that. So that's how you do scientific notation in a calculator. So I'm saying 2.998 second, comma, 8 divided by 1.110 second, comma, 6, and I get basically 270 meters, which is what we thought about. Our estimate was 300, we got 270, so we feel pretty good about that answer. 270 meters is pretty far. That's going to be about 3 football fields. So if you turn on a radio and you tune it to 1110 AM and you listen to WVT, you have got these 270 meter waves passing through the antenna of that radio. The interesting thing about it is that turning on the radio didn't make those waves come there. The radio just detects them once it's turned on. Those waves and all the other waves in the electromagnetic spectrum are around us all the time. And of course they're largely, for most parts of the spectrum, quite harmless for us, but they're there all the time. All right. Moving on here, this is a nice picture of some waves and some illustration of different wavelengths and stuff. So take a close look at those. Usually the book will always have prettier pictures than I can draw. So again, there's all kinds of other types of radiation in the electromagnetic spectrum. Sometimes we'll call electromagnetic radiation EMR generally. So if you hear EMR, that means electromagnetic radiation. So here are some examples of different types of radiation that we have here. I'll blow that up a little bit. And so you see on the bottom here, we've got a wavelength scale, and that wavelength scale is going from very long wavelengths down here, like 1,000 meters, to very small or very short wavelengths. 10 to the 12th, it would be called 10 to the negative 12th would be a picometer, which is really, really small. If you're talking about the size of an atom, you're kind of like down here is about the size of an atom, around 10 to the negative 9th, 10 to the negative 10th. So you're talking about really, really small things. And there's a relationship, we have the one relationship where we say that lambda times nu is equal to c. So as wavelength gets longer, the frequency becomes less. So this long wavelength end down here, this is the high frequency end, and this is the low frequency end. Again, that's the general formula. Another formula we haven't talked about yet is Planck's formula, which is E equals h nu, which is the frequency, basically says that the energy of the particle of light, thinking of them as particles of light, which we call photons, that energy is going to increase as the frequency increases. That means it'll decrease as the wavelength increases. So down at this end is our high energy. And you see some things here that are dangerous to us. So cosmic rays, X-rays, for example, are the sort of things that we tend to try to avoid exposure to. X-rays obviously have quite a bit of utility for medical diagnosis, as does a PET scan, as they point out there, that uses gamma rays. But when you're undergoing such things, you take precautions. You might, in an X-ray, wear a lead blanket to cover most of your body while you're getting, say, your teeth X-rayed. Then as you move on up into the ultraviolet, if you've ever had someone, a dentist, use do something to fix your tooth, put a filling in or whatever, and use a light that looks kind of bluish light in your mouth for a while, that's what's called dental curing. Basically, what that light is doing, that ultraviolet light, is promoting a chemical reaction in the stuff that they're putting in your teeth there, and that's causing a kind of reaction usually called cross-linking, where polymers solidify, and so it's basically like you can think of it as making the glue dry really fast. And then you have this itty-bitty region in the middle right here, this teeny tiny little part of it here, which is the visible light, which is where human eyes are actually evolved so that we can see in that region. And then going on, you have infrared, like our remote, and then down here the microwave level, which is usually what cell phones operate on, and what our Wi-Fi's work on, and what weather radar, for example, or any kind of radar works on, and what microwave ovens work on. And then finally on down into the what we call TV or radio area, which are long waves that are very, very low in energy. So we tend to think the ones that are the high energy ones are really only dangerous. So the idea that cell phones are causing problems, it doesn't seem to be supported much about like that. Now you might say, well, wait a minute. Why can't I stick my hand in a microwave oven and run it for a while? And so I need to explain to you a little bit how microwave ovens work. So for each of these regions on the spectrum, they have a way that they interact with matter. And the way the microwave region of the spectrum interacts with matter is it causes molecules to rotate, and which just means spin like a top. And microwave ovens are tuned so that they rotate. Well, think about it a second. If you were trying to heat up food, can you think of a molecule that would be present in every type of food we might have that you could tune your thing to rotate so that would heat that up. And if you're thinking of the molecule water, you'd be right. Yeah, the microwave ovens are tuned to make water molecules rotate. As the water molecules rotate, they bump into other molecules, and that bump is just like, friction, just like rubbing two sticks together, and you wind up generating heat from every water molecule out. And so that's why a microwave oven will cook your lunch or whatever, or warm it up at least, by cooking it from every water molecule out. So your cell phone, though, the power level is pretty low, so I don't think you're cooking your brains while you're using a cell phone. All right, so here is an example of the kind of question we talked about, where we're going to be using one of these equations, and we're going to try to calculate some other things that we know. So we talk about a sodium street light. It gives off a yellow light that's characteristic of an excited sodium atom, and that wavelength is 585 nanometers. What's the frequency of the light? So if we want to get the frequency here, we've taken the equation C equals lambda times nu. We rearranged it so that nu is equal to C over lambda. And of course, the joke is, hi guys, what's new? The answer, C over lambda. So we're going to plug in here our speed of light. So the speed of light, again, we said was 2.998 times 10 to the 8th meters per second, or meters seconds to the minus 1. The wavelength here, we've got 589 nanometers. We're going to write 589, and then we're going to multiply that by 10 to the negative 9th meters, where that times 10 to the negative 9th stands in for our nano. So that we can literally plug that in the calculator. When we do that, meters and meters are going to cancel out. We'll have seconds to the minus 1, which is hertz. So 2.998 second, comma 8 divided by 589 second, comma negative 9. And let's wait a second. Maybe before we hit enter, let's think about this. So 2.998 is basically 3. 589, we could think of that as 600. 3 divided by 600, well, that's a little hard, but 3 over 6 would be 0.5, right? 3 over 60 would be 0.05. 3 over 600 is 0.005. So my estimate, this part I'm going to say is 0.005. And then I have 10 to the 8th divided by 10 to the 9th. So I'm going to have 10 to the 8th minus negative 9. So that's going to be 0.005 times 10 to the 17th, right? 8 minus 9 is the same as 8 plus 9 is 17. All right, so I want to get this so it's in the right thing. So if I go 1, 2, 3 that way, I'm multiplying that by 10 to the third, so I have to divide the 10 to the power. I have to basically subtract 3 off of that. So that's 5 times 10 to the 14 seconds to minus 1. So that's my estimate. Let's see how I do. Hitting enter on my calculator, I get 5.10 times 10 to the 14th seconds to the minus 1. So not far off at all. Again, the advantage of doing an estimate like that is that if we do that estimate, we're going to be able to tell whether our answer is reasonable or not. I kind of have a theory about chemistry classes that the students who do well might not be the students who get the problem right the first time, but are the students who recognize that an answer just can't make sense based on what their estimate and their conceptual understanding of the problem would be. So the skill of estimating here, I really hope that you think about. So anyway, they show us their solution down here, and you'll see some more examples later on of stuff. All right, so again, this is getting to the energy that's contained in these particles of light, and there was a problem That's usually referred to as blackbody radiation or the ultraviolet catastrophe. And basically, what it did was it talked about so in the ultraviolet catastrophe or in blackbody radiation, if you heat up a metallic object, and I had the advantage of growing up having a lot of opportunities to set things on fire, and we had a wood-burning stove, and I frequently would deal with that. And I had this big metal rod that I would poke the wood with, and if I left that rod in the fire, I would see the tip of it would get red, and then eventually it would even get white. And that kind of emission of color, emission of light from that piece of metal due to heat is exactly what this blackbody radiation problem was. And the problem was basically that if you tried to explain the color of the light that was being emitted based on the temperature of the metal, the existing models that they had to explain this, that were based on the wave model of light, just didn't work. I mean, they just gave ridiculous results, which is why they called it the ultraviolet catastrophe. And if you look in your book around figure 3.9, you can see discussion of that. So Max Planck decided that maybe we can think about light as a particle, and he came up with this idea that the energy contained in that particle of light, it would be a little packet of light, and that packet would have the energy of h nu, okay, where h was a constant of that, and the n comes from the idea that you could have multiple packets of those energies. So I could have 1, 2, 3, 4. I couldn't have 3.5, right? But I could have 3 or 4, for example, photons emitted that would give off the energy related to that. That energy can get related back, again, you've got a frequency there. That's our frequency right there. So we can relate that back to the wavelength and the color of light and so on. So the equation generally is known as E equals h nu. If I plug in, as we'll see on a subsequent slide, if I take nu is equal to c over lambda, I can put this in for nu and get hc over lambda for that. So the energy, and this is the energy of a photon, of one photon, a photon being the particle of light, will be calculated by that. Now, that was good work by Planck's part, eventually got him a Nobel Prize. The next thing that came along was something called the photoelectric effect, and looking over in your book there is, let's see, if you go down further, there's a subsection called the photoelectric effect, and figure 3.11, which we'll see an image of later on, kind of explains it. To me, the way I've always thought about this was this idea. If I think about a graph and the energy that's going to be given off versus the frequency of the light that's being shown. So the idea is basically you got a piece of metal. So this is some metal, and we have light impinging on it, right? So we're shining a light on it. And what can happen at some point is that you get electrons given off, and those electrons would be like an electric current. So this is, for example, basically a light-powered battery or a light-powered cell or a solar cell. Basically works using this process, that the light that's in solar radiation is enough to cause electrons to be ejected from these the atoms of these metals, and that sets up an electron flow. Now, what you would normally think is the more light, the more energy. And while that's true, it also turns out that the frequency has a very, very big effect on this. So here is zero energy. I'm going to draw it up here above the line just to illustrate it. And what was observed was that if your frequency was low, no electrons would be generated. Then all of a sudden, you reach a certain point that you would start having more energy in those electrons that were ejected. So below a certain value, nothing happened. When you went above it, not only did the electrons get ejected, they got more energy in a very nice straight line kind of relationship. And folks were having trouble figuring out how this happened. And what happened was there was this guy who had finished his graduate degree in physics and had become a patent clerk, a little government job in Switzerland. And his name was Albert Einstein. And in 1905, he published 5 very famous papers. One of those papers explained the photoelectric effect by taking Planck's idea of quantized energy, or the idea of photons, and saying that, okay, that below the point where the ejection of electrons starts happening, so in this region right here, there's not enough energy. And remember that energy is equal to Planck's constant times the frequency to overcome the what we know now as the ionization energy, the energy that it takes to get rid of the electron, to take an electron away. And then above that, you've met the ionization energy, and as you have any extra energy you have gets translated into more energetic electrons. So it was a big deal in terms of getting the photon idea of light, the particle idea of light, to be accepted more broadly, and it won Albert Einstein the 1920 Nobel Prize in Physics. One of the reasons he got the Nobel Prize for that one was that wasn't as controversial. 2 of those other 5 papers were about relativity, and Einstein's theory of special and general relativity were just too far out there, everyone thought, to give him a Nobel Prize for, although they've held up pretty well as well. So here's a summary again of this idea. And so as the view of light, that you can think of it as a particle, was growing, while at the same time there were other phenomena of light that had to be explained by evoking a wave idea, led to this idea of wave-particle duality, that we don't know what light really is, but sometimes it acts like a wave, sometimes it acts like a particle. And so here is the figure. This is figure 311 in your book, that explains this ejection of light. And you see 700 nanometers. This is a long wavelength, a lower frequency, right? So this is lower frequency, and of course this is the higher frequency going from one end to the other, and the waves represent the light coming in. We haven't talked about it, but you remember perhaps hearing Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. That's how you remember the spectrum. If you think about the visible spectrum, right on the other side of violet is the ultraviolet, which we know is potentially dangerous, and on the other side of red is the infrared. So we know that as we're going this way, frequency is increasing, wavelength is decreasing. Going that way, energy is increasing. So the 400 nanometer purple light here has the highest energy, and the 700 nanometer red light has the lowest energy of those 3 photons that we're seeing on this slide. All right, so if we go back now to calculate that, or if we're going to look at a slightly different thing. So we're looking at a neon sign, and you've seen probably neon lights before. They're not always neon, but sometimes there are other gases. But I used to have to go out and change the marquee at the Rogers Theater every Thursday night so folks would know what was going to be at the one screen theater that I worked at in high school in Shelby, North Carolina, and I had to be very careful not to break those neon lights or I would get into serious trouble. Anyway, but the bright neon lights that we see that are very colorful in the city and other places, that light is caused by passing electricity through neon gas or some other gas, and that electricity excites the electrons in atoms up to higher energy levels, and then when they drop back down, they emit light of a certain wavelength or a certain frequency. So we're told that the wavelength is 640, and we're asked to calculate the energy. So we use that version of the equation where E is hc over lambda that we arrived at before. You can see we have Planck's constant here, we have the speed of light here, here we have the wavelength, and then this is our conversion factor going from nanometers to meters. And if we plug that in our calculators, we come out with an energy of 3.10 times 10 to the negative 19 joules. And again, this is a great chance for you to plug this kind of numbers into your calculator. Make sure you know how to work your calculator and get the right answer with this, and keep working at that till you get the right answer. All right, so again, the idea is that these emission lines consist of a single wavelength, and that because they're a single wavelength, that means that the energy is quantized, and the ability to explain why it should only be one particular wavelength in that line and not a continuous spectrum, well, that created another problem. So let's look at spectra here a little bit. Let's see. All right, seem to be losing stuff here. I think it's probably just slow loads on the thing here. So I'm gonna give it a second. And in fact, what we'll do is we'll just break this one at this point and pick it back up